So last time we saw linear regression, right, with one variable only, right? So I think everybody knows where the videos are, right? You attended, right, to that those stuff. So what?
Graphical note.
Somewhere it is just I mean the data science and machine learning channel is there, right? Just see, subscribe to the channel, see the updated videos over there. Okay, I'm adding it over there, linear regression. So what we did last time with with only one variable, we found out the relationship between x and y. Right. This was just a recap. So if I recap. For this should be this one. Okay, remember this? So we created x and y, and then later on we found the relationship between x and y. Right. This was the first stint with linear regression. Now let's proceed further. Okay, so that was simple linear regression. Simple linear regression because there were only one feature in the feature vector. Remember, this was the feature vector. Just a recap to know everything. All right. So we had this feature vector. Okay, a number of features too. Okay, you can see here there were two features. Okay, you can, I mean, later, and actually we did it with one feature only later on. Got it, right? That is a simple linear regression. Simple regression means the feature vector will have only one feature. Okay, now we'll see okay, multivariate polynomial regression. That means we have multiple variables here. Okay, the feature vector will have multiple variables. Okay, now a few important things to understand is that okay, the few important thing to understand is here, if this is only with one feature. Okay, now if the number of features increase, okay, so you have one feature and you are finding the relationship between x and y, right? Now if the number of features increase, that is we are getting into a multivariate case. Okay, multiple features. So the separator also becomes little complex. Not the separator, the line which becomes a predictor also becomes little complex. Okay, let's now see that. Huh? Let's check import numpy as okay. So what we'll have here, we'll have two features. Okay, we'll have two features. Unlike earlier, we'll have two features. Then we'll see the line here. Quickly, we'll do. Okay, we had okay, so okay, and okay, we have that. And earlier we saw a straight line feature, right? All the feature was along a straight line. Okay, now we'll see a little complex feature. I'll use my projections to show that. Okay. So this is your x and y axis. Okay, and earlier we our x features along one direction, right? I mean it was pretty much it was in this is your x, this is your y. Okay, now what will happen? We are generating data which looks like this. Understood, right? Okay, so we are generating data which looks like this. As of, let me first show with only one variable, x only, but the data is not straight line here. It is this way. Okay, it is little curvy here. Okay, that's what you see. It is curvy here. So straight line is definitely okay. A straight line is definitely not the best fit here. Understood, right? You have a polynomial. This is a straight line, linear line. This is a polynomial degree line. So polynomial degree line is a better fit for this particular case. Right now, the question is how. The question is what are the possibilities? Last time we discussed what are the possibilities of straight line, that is based on theta 0 theta 1, that was huge, right? Now also the possibilities of polynomial degree 1 degree 2, understood? This is maybe degree 2 line, this can be degree 3 line, right? This can be degree 4 line, far more convoluted also. Okay, so the possibilities of this degree of these lines are quite huge. Okay, and we'll try to find out which is the best degree line which suits our data. Okay, let's generate the data. We are generating data from 0 to 1, 10,000. Y is equal to, see, I'm generating a polynomial degree line, no? X into X plus 5X, 5 into X plus 100. You saw, we have X, we have Y, we have polynomial degree line. Now, okay, now we have, this is my X, right? This is my Y. Okay, so a few things to understand here. This is same as multivariate. I just took this example because it is easier to understand. Okay, so what we need to find out after the final prediction, after the okay, so we have this is what you have to do. We have to find the hypothesis. I mean, we have to find the algorithm here. We have eventually our algorithm will predict this formula, right? The coefficient here, the intercept here, it should find all these values, isn't it? Okay, remember in the earlier case, just keep comparing with earlier case, our algorithm finally predicted 5 and 44, isn't it? 5 and 44, sorry, 5 and 44. Okay, so we predicted 5 and 44, right? 5. So in this case, what will you predict? In this case, what will you predict? We'll predict 2, 5 and 100. We know that answer as of now. Okay, just if had you not been knowing the answer and you know it's a degree 2, your line should be a degree 2 polynomial. What is that you have to predict? You have to predict these coefficients, right? These are your theta vector. The theta consists of 2 and 5, right? And 100. These are the values you should be finding. You should be predicting out, right? So what you have to do, you have to find out the coefficient of x squared, the coefficient of x, and coefficient of the this intercept value. So what you need to do, you need to convert this x into polynomial degree actually. If I see what is that you have to find out, you have to find the coefficient of x square, coefficient of x, and intercept, right? These all values you need to find out. This is my x data, this is my y data, right? This is my x data and this is my y data, the crosses that you see here, right? And to find what we intend to find, we intend to find the best representation of it. Is straight line the best representation of it? This could be a good representation of it, the red line or the purple line, we don't know now. Is it clear? So what we need to do is we need to convert this x data into polynomial features now, polynomial data, so that we can find coefficients for that. Let me show it, it will be clear.
So here I think the values which are coming in the output of x and y.
Which one? This one?
Yeah.
This one I'm generating in space. Boolean space is that I'll generate between 0 and 1, right? Okay, 0 and 0 and 1, I'm between 0 and 1, I'm generating 10,000 data. Okay.
So it won't show all the outputs.
It will show. I mean, it's showing dot dot dot, right? So sklearn. Okay, so we have this polynomial feature. See what this does. We are creating these polynomial features and we want to convert this data into polynomial features of degree 2. Okay, see this. Oh. See this. What is this? The first line is one, whatever is data, right? What this polynomial feature does is this is 1, this is x, this is x squared. Understood, right? Okay, since we gave degree 2 here, okay, maybe okay, say for example, you have this very simple data test. NP.
This sklearn is a library.
sklearn is a scikit-learn library. Okay, see this is arrange 10 shape minus 1, whole dot fit transform t. You see this? Do you understand it? What is happening? So this, what is this t? This t is 0, 1, 2, 3, 4, 9. Understood, right? This is the data. When you pass this data to this fit transform, what is fit transform? This is known as transformer, which is changing your data from one format to another format. Okay, changing your data from one format to another format. So what is this doing? This is changing the data, which is like 1, 2, 3, 4, like this is the x. It is changing data for x raised to the power 0, x raised to the power 1, x raised to the power 2. Understood, right? Because what is your final objective? Your final objective is to find coefficient for this column, coefficient for this column, coefficient for this column. Right? So that is a linear regression, right? You are finding coefficient for all the columns. Then, and once you get the best coefficient for all the columns, you just pass any value for those columns, you'll get the result. Right? So that is what is happening here. Okay, so this understood what is this polynomial features? This is a transformers. Transformers which changes your data from one format to another format. Right? Polynomial features the transformer which changes your data from one format to another format. Okay, what it is doing, it is changing your one-dimensional data like this to data which looks like this. Got it, right?
It is up to square only because our polynomial is
second degree. Because we gave here second degree. If you want, you can make it high degree as well. Understood, right? So this is my x now. Okay.
So Ankit, like how you input it from sklearn input polynomial features. So while doing the programming, how do we get to like understand that from where which functions to be?
I'll show you that entire list. Entire list. There's a pre-processing library. If you do tab, it will show. Or sometimes it doesn't show. It should show. Just pre-process. You'll get to know once you do all the things. You'll get to know what is that. So now, understood what has happened. Your x has now been converted to this. X raised to the power 0, x raised to the power 1, x raised to the power 2. Okay, because we have to find coefficients of this. Is it clear? Okay, now Okay. Now, um, okay, you have created empty brain, then you are passing here x and y. See here, it is doing the training here for degree 2, right? This is because you have now passed degree 2 data here. Linear regression will try to find degree 2 coefficients. Understood, right? Linear regression will now try to find degree 2 coefficients. So if I do LR dot coefficient, you can see here it is finding all the coefficients, right? 5 for x, 2 for, and if you do LR dot intercept. Understood? See, this is the value, right? 5, the values was 5x plus 2x square was there, say 2x square, 5x and 100.
Okay.
So it actually predicted that. Okay.
It is predicting or taking from that equation?
No, it's no, we are just passing x and y, right? It is predicting that. It is predicting the relationship between them. Okay.
Can you once again show from the top how we exactly?
So you generated data as similar to last time. We generated a data x and y. Okay. Okay, we generated the data x and y. Okay, then you have this. I mean, like this is where x, this is y. Then you have sklearn pre-processing. Okay, and you have polynomial features. I mean, we are importing this library. After that, we are creating a transformer. What is this transformer? Which will change your data from one format to another format. Okay, we'll basically sometimes we might have to convert your data. Might be in any range. We might have to convert between 0 and 1. We'll use transformer there. If you want, you can note it down. Transformer is something which changes the data from one format to another format.
The transformer means like if from m cross n it will change m and n, right?
No, I mean, in this case, it is actually one column. It is converting one column of data into 3 columns of data. Okay.
Yeah, so means so m cross n, if n comma 0 is there, so it might be 5 comma 5 like that. Matrix, right?
No, many other things. So transformer can actually convert the data between 0 and 1 also. Okay, so image data processing and all that.
So this polynomial feature 2, it is converting it into 0, 1 and 2.
0, 1 and 2 degrees. Okay, understood, right? You are generating 0 because you want coefficients for them. If you want higher degrees, you pass one more.
Yeah. If you do 3, then 4 columns.
Exactly. If 3, 4 columns will come and you will find coefficient for those 4 columns. This is very similar to, because if you understood, right? If you are degree 2, if you're trying to plot a degree 2 polynomial, your equation needs to be curvy. So this is 2x squared plus 5x plus 100. It predicted that.
And after that, when the statement again, you can scroll it. Yes. So x dot reshape minus 1 comma 1. What is this doing? Minus 1 comma 1.
This is bringing. I mean, this is one-dimensional data. Okay, if you do minus 1 comma 1, it will actually bring them in the. I mean, convert them into rows of column.
Rows of?
Rows actually. Minus 1 comma 1 means one column and derive the number of rows. Got it, right? So let's do one more problem with this one. Some real data. This I have been simulating some data to explain some of the concepts. Let me do with some real data. So I'll use house price data now. Okay, I have this data in my GitHub.
Notebook is not opening on my machine.
Which one?
Token authentication is available, something like that.
The tab, it's a box is coming. Wherever you run Jupyter Notebook, right, the command, there a long string will be there.
Yes.
Copy that.
I copied that one as well.
The full might not be copying the full one. Okay. So we have this house rental CSV. So I'll pick up this data. Okay, as you can see, import. Okay, so we have loaded this house data. Okay, so you can see here, basically there is a, I mean, we could have used this guy as an index column, so you can mention it here.
Only before file name we used to add R, right? Before adding file name or.
I mean, if like in this case.
No, what is that for?
There is a raw string.
So is it a good practice to add before link and before files everything?
Link, yeah, you can give it. I mean, it's always a safer practice. If you face any problem, just add it over there.
Only the R.
R for raw string. Treat the entire text as raw string. Okay, do you see the house price data here? And how many columns are here? Okay, how many columns are here? 7 column, right? So what is the feature data here? The feature data is this, right? This is the target data here. Is it clear to everybody? Understood, right? This is the feature data. This is the target data. Okay, now what we have to do, we have to train this is the historical data, right? We have to train the model. Okay, so let's see now one by one. Feature data can always be represented by X. Right, this is your X feature data and this is your Y target data. Now let's use linear regression. Okay, and before doing that, okay, let's understand two more things here. Okay, please pay attention. Now, the first thing is, this is okay. So we will basically what we'll try to do. We'll try to find coefficient for each of the column. Understood, right? Simply, if we take simplest linear regression, okay, without converting this data into degree, higher degree and all that, what is that we'll try to do? We'll try to find coefficient for all the different columns. Do you agree with this? Right? That is what linear regression does. Okay, so what is the what is one of the possibility? Okay, one possibility is, okay, degree one. I mean, trying it out for degree one, right? I mean, degree one means not adding, not passing through a polynomial feature transformer to convert to degree two. Okay, just to give a heads up here, what happens when you do that? Okay, that will clear. So if you have from sklearn dot reprocessing import, suppose you have this, and you pass pul is equal to polynomial features, you pass there 2. Okay, you pass 2 here. Then if you do this pol dot fit transform, if I pass my x, remember how many columns my x had? X had my 1, 2, 3, 4, 5, 6 columns. The last one was not there in x. I mean, x means x didn't have the price column, right? But feature vector. Okay.
And then first would also come, right?
Huh?
The index would not be counted.
No, index will come.
It's a part of the data.
But it is not. It is the showing the data. It is. Do you think index will make an important decision? Contribute something in making a decision? No, it's just an index. Okay, if I pass this x here, see the data is now converted to degree 2. You have a lot of columns here, right? See, now earlier 1, 2, 3, 4, 5, 6 column got converted to 28 columns. Did you notice this? 6 column gets converted to 28 columns. So this is with degree 2. If I make it degree 3, what will happen? 84. So what I'm trying to say here is, what are the various ways you can plot this linear regression? One is degree 1, that means the simple linear regression. One is you can add derived features out of it, degree 2, degree 3. Okay, so this first one is this is the possibility, degree 1. Second one is degree 2. Third one is degree 3, and so on, and many more. Understood, right? Okay, so
I think in mine, degree 2, degree 3 it is coming 120. Degree 2 is coming.
And maybe you are using price column there. You are using price column, that's why.
So even here it is in price column.
No, I dropped the price column in my X. On that way it is coming. You can check. Just check something mistake you have done. Okay. So understood, right, everybody? See, let's get this understanding clear. So you have, what you're trying to do, you're trying to predict a line or a polynomial degree line, right? What you're trying to do, you are trying to either predict a straight line. Okay, so each data, how is each data represented here? Suppose this is one house. This is some dimension. This is one house. How is each house represented? Each house is represented by a x vector, isn't it? Okay, and what are the parameters? Say, talking about the 648 house, you have upstairs. Be seated. Okay, so you have 1376. This is one thing. 6, 7, 3, 2, 1. This is a feature vector. Understood, right? If you try to plot, see, if you have a 2-dimension space, if you try to plot a point, it will be x comma y, isn't it? Is it clear? If you have a 1, 2, 3, 4, 5, 6-dimension space, it will be plotted by this, right? Just extrapolate here. So what you have to do, you have to create a hyperplane. Hyperplane means a line means one variable is there. Hyperplane means there is 6 variable. I mean, it can be more than 3 anything. Like we are trying to create a hyperplane which acts as a predictor. Understood, right? There you'll be passing all the values of this and it will predict you the price. Okay. Now, okay, let's see now. Okay, so that's what we'll do. We are using polynomial degree. So, what is our next task? Next task is to identify which one of them, like degree 1 is better, or degree 2 is better, or degree 3 is better, or which one is better. So basically, you have to validate the algorithm that you are choosing. So you need to divide your data into test and train data. Understood, right? This is known as validation. You have to break down your data into test and train. So you have another API for that from sklearn dot model selection import train test split x comma y train plus split. Okay, so you basically have to make it train x test x train y this one x comma y, right? You have this. What this did is they divided the data into 80-20 ratio. Okay, say earlier, what was my x shape? It was 645, right? What is my train x? Okay, understood, right? It is not completely, and it is test x shape. Okay, so you divided the training data and the testing data, I mean the feature data and the target data into two parts. One part you will use for training, other part which you have not shown the data so far, you will use for validating, right? Okay, then we'll use validation data as well. So let's use this LR is equal to from sklearn dot linear model import linear regression. LR is equal to linear regression. Train X. This is for training the model. Okay. Then train Y. Right? X and Y you are passing. And what is the degree here? 1 degree first we are trying. Understood, everybody? Okay, we are trying to predict if a straight hyperplane is better or a complex hyperplane. Okay. So the training is done. We want to see how is the results. How do we validate it? We validate it with unknown data and see how do you validate. Suppose you are writing an examination, and suppose you are writing an examination, and she is a examination character who corrects the copy. How do you validate his results? You will have some another copy of correct results, right? We will compare how similar is your result with that result, isn't it? The same process will take it here. We have another copy. You have given train examples to train it. You have the sample copy and all this for him to study. After he has done the study, you want to check how good is his intelligence built now. So what would you do? You will give him the the test data, right? And you will try to give responses to that. And based on your responses, you will compare. Okay, which one is better? I mean, how closer have you got, right? And based on that, you can say you're getting. Got it, right? So that based on that one, you will mark him, okay, 80% of correct result, 90% of correct. Here also, this training is done here. Now you want to validate how close is to correct results. For that, you have sklearn matrices. Matrices means here all the measuring things are there. Okay, how do you? Okay, so you remember we have earlier seen mean squared error. What is mean squared error? Mean squared error was for a particular. Okay, we have seen this formula, right? 1 by m sigma of I is equal to 0 to m. Okay, predicted value minus actual value. I mean, rather, h theta x, yeah, it will be y square of it. This is what you've seen earlier, right? This is the root mean square error. Remember that? Okay, so what is it? This is the cost function of it. That means how far, just imagine what I'm trying to say here. Suppose you are talking about 2-degree line. Suppose this is the case. This is the line that you are predicting, and this is the actual point. Understood, right? So for this point, the actual prediction, this is your x, this is your y. For this point, the actual prediction will come here, isn't it? Right? So the difference between this is your y, this is your actual y, this is your h theta x, this is the prediction, and the difference between them is this much. Okay, so what you're doing, you are squaring it up and summing all the differences, all the errors. Is it clear? This is the cost function of this straight line, right? You want to see which one is better. Okay, this is one technique. Okay, and the same thing. Okay. Okay, so let me show you how. Okay, so these are all part of your scikit-learn. If you click here matrices, you can see we are trying to do regression, right? So you have all these varieties here. Okay, we're trying to now mean squared error. Okay, so how do you do that? So this is your actual prediction. This is your y2. This is your y prediction, and it will return you that. Let's see. So lr dot predict. What is that you are predicting? Test x y pred. Understood this? This is the prediction here. Okay, so what let's see what is the prediction. See, this is the house prices one by one. Okay, let me show you first 5 only. Right, and test x. Okay, this is first 5 only. Can you see this? So for this house, the cost was predicted was this much. Understood? Right? For the second house, the cost predicted this much. What was the actual cost? We need to know the actual cost also, right? To see what is the actual cost is in your test y. This is the actual cost, right? That's what we did. We splitted the data into train and test, right? So this is the training is training y, test x, test y, right? Training y means you divided the training data into 2 parts. Okay, x means the feature data, y means the target data. Okay, x means the feature data, y means the target data. Okay, so that is why this is the training part. This is the test x we tested, and y is your actual result. So this y is your actual result. We basically want to see only 5. So what does it mean? To see the data. The first house was of predicted it. The house price was 55,000. It is predicting 91,000. Second house was 98,000, it is predicting 68,000. Third price was 36,000, it is predicting 29,000. Understood, right? Okay. Fourth price was 63,000, it is 82,000. Third price was 90,000, it is predicting 70,000. Right? Of course, there is an error here. Not so close it is getting. That's because, maybe degree 2 is better. We are using degree 1 now. Okay. But how do you compare and how do you conclude what is the error for this entire algorithm? You can use this guy. Mean squared error. What was the first thing? Y true, right? See, you're passing Y true here. Y true. So test Y versus Y bed. Whatever result you get, mean squared error. This is a squared error anyway. So let me mean absolute error. I can do. This is a squared error actually. You have to underscore and square root of it. So I'll also use this guy. Mean absolute error. This is a squared error. It's not doing a square root there. No? Mean absolute error. Test 1. Right. So you can see this is the usual difference then between the actual price and predicted price for this entire thing. Understood, right? This is the measuring parameter, you can say. Now you can try degree 2 polynomial. Okay, let me do that. You go through this video one more time. Okay, you need to. Okay, and feel free to ask the questions because see, I don't want to touch superficially. That's why I'm going little deep. And when it gets little deep, I see some expression in the face. Okay, so don't worry. Okay, go through that one more time. Okay, go through this one more time. So this is degree 1, as we discussed earlier.
What is degree 1 and degree 2?
You could have asked that earlier also, right? So degree 1 means when you say a equation of a line, this is suppose ax plus b. This is what is the degree of x? M1, right? Then you have ax square plus bx plus c. This is degree 2.
Maximum power.
Right, maximum power. So
But how do you find out from degree 1 to degree 2?
Yeah, that is why what you have to do, you have to convert your data. See, what you have to do, you have to convert. See, for this data, you had only one value of x. For not yet connected through inverter.
You have to multiply the whole equation by x
Hmm?
to get the degree 2.
No, see, suppose the previous example that I took, okay, you have only one column, right? X is only one column, right? So so X is only one column, and you did simple linear regression for predictive straight line. This was for the first one. Check. So here you can see this is straight line that you are predicting. So only one column is sufficient, isn't it? One X column is sufficient. This point is clear. For a X, what you do, you try to predict this A and B, isn't it? Okay. Now it's A and B using linear regression. Now you want to predict. See, and you remember our data was not linear. Our data was like this. Right. It's not a linear data, not a straight line data, right? So maybe straight line, if it is trying to predict this, the loss is very much. The mean square error or mean error is very much. The mean error is different between this guy, this guy, this guy. This error is pretty much. Compared to if you try to predict line, which is more like this, it will be a better representation of the data. Right? It is a better representation of the data. Now, Okay, now what you need to do, we need to find, if that is the case, we think that, degree 2 polynomial will better. Degree 2 polynomial means it is more curvy. Degree 3 polynomial, it is, understand this time, right? Degree 3 polynomial, it is further curvy. Degree 2 is this, degree 3 can be this, degree 13 can be like this. Understood, right? But to find degree 13 polynomial, you have to convert the data to all possible degrees and find their coefficients. Okay, you have to convert the data into all possible degrees and find their coefficient. So that is what we did earlier. Now also what we will do this thing, we'll convert whatever x data we have, right? We'll convert that into degree 2. As of now it is degree 1, right? And this is a cost here. Let's see with degree 2. Okay, and then we'll see the cost. And remember, this cost we are finding out with respect to unseen data, unshown data. Okay.
But one thing, if degree 1 is a straight line, how sure it is like degree 2 will be not your straight line and it will be the actual data.
See, what is degree 2 line basically? Degree 2 line means, okay, this is your, what is degree 1? Y is equal to x, right? I mean some coefficient this. So degree 2 is y is equal to x square. What is the curve for x square? X square curve is like this, isn't it? Huh?
It will be one side, no, not be a wave.
One side I was trying to draw that only. It will be like this, right? So if it is x square plus x, then it can be little wavy, like this. Understood, right? X square minus x. So with increasing the degree of polynomial, it will get more and more curvy.
Yeah, but the degree of x will be only x square, right?
Degree 2 polynomial does not mean you will have only one parameter. Like you remember the previous example that I took. We had one column.
Can you explain with respect to the straight line how it will become a curve?
So
Y is equal to mx plus c.
This is a straight line, right? This is a degree 2 line somewhere. It won't be like this. Somewhere degree 2 line. This is a degree 3 line. This is okay. So if you have x square minus x, it will be like this, right? Something like this. Okay, so the more degree you add, the more curvy it gets. Okay, you can try plotting this with matplotlib with different degrees of a line, right? The more degree you add, I mean that's typically how y varies with respect to x. There's no magic over there. If y increases then decreases a bit, it becomes curvy. Okay, and if you think that, house price is better represented like this, understood, right? Then degree 2 is better sometimes. Is it clear? Okay, so with increasing degree of line, your line becomes more curvy. That means maybe line is becoming a better predictor. Okay, so let's see this data again. Okay, so we have now tested this with 1 degree, but remember now the x variable is not for 1 dimension. It was 6-dimension variable, right? Just imagine it's, don't imagine, actually it will be a vector in a 6-dimension space, and you are creating a line which separates it. Okay, the thing is, just imagine in 2-dimension space and extrapolate in 6-dimension space. Okay, how do you imagine in 2-dimension space, right? You have to imagine, you have to do this actually. Without that, it is really impossible. So if you have a 2-dimension space, x and y, okay, and this is one point, it will be represented by 2 data, right? X and y. Just imagine that dimension changes from 2 to 6. Then this point will be represented by 6 points. Is it clear? Right. So now what we are trying to do, we are now trying to convert the data that we have seen earlier. We have seen x, right, and y. We'll now convert this into degree 2 and then compute the mean absolute error. Then we'll see which one is better. Okay. So tell me one thing. If you have 3 points, if you have in this scale itself, you have 3 points. One is there, one. we have these 3 points. Okay, this x and y, c and d and a, b, you have these 3 points. Now, what is the degree of line which, what is the maximum degree of line that is required to touch all these 3 points? Remember, class 6. What is, suppose you have 3 points, what is the maximum degree of line that is required to touch all these 3 points? Yes. It's always k minus 1. Right? So if you have 10,000 points, what is the maximum degree of line that is minus 1, right? Okay, okay, so just know this now. Okay, so that is required. But do you think a line with that much high degree is a better answer? No, because your predicted line should always be simple. If you are getting into a line which is touching all the points, then you are getting into case of overfitting. Overfitting means it will touch all the points. Okay, it will, for the training data it will work well, but for new data it will not work well. Understood what is overfitting? Overfitting means, of course, you can predict a line which is touching all the points, like it is becoming like this and all that. Okay, by increasing the degree of polynomial. But on doing so, what is happening? You are getting into case of overfitting. Okay, overfitting means training error is less. Okay, training error is less. What is training errors? If I would have calculated the mean absolute error for train y and y pred on the train y, right? It will be less, but for unknown data, it will be very high. Okay, let me create degree 2 here. From sklearn dot pre-processing import what degree 2 we are interested now, right? So convert this x Is it fine? We converted this x into degree 2. If you do x dot shape, okay. Now you need to divide the data into train and test, right? Because train data should also have that much same part of the data. Train x, test x, train y, test y, and test split. X and y. Okay, so you do this LR linear regression, LR dot fit train x. Right? Y pred LR dot predict test x. Okay, so
one more thing, how linear regression will work in multiple dimensional data?
It is multiple dimension data only, right?
But linear regression is just finding a straight line between.
No. That's what I'm saying, right? Linear regression also means polynomial degree. Linear regression also means in multi-dimensional space, ax plus by plus cz. This is also linear regression actually. Okay, just don't think in terms of two dimension. Okay, so a straight line in a hyperplane means okay, a plane line ax plus vy, a plane. So that is how it will work actually. Say in this case, right? What in the first case it was a, say I missed out showing it, I guess. So in the first case, how many coefficients will it be generating? Right here we calculated this value, right? Let me show it in this case, then I will revert back otherwise. This is the predict, right? Mean absolute error test y pred. Can you see this? Earlier, what was the errors? 1400 something or 1400 to 566. Now the error is 1600. So which one is better? Can you see the error is 1600 something now? Earlier it was 1400 something, 14,000 something. So which is the error? Which is the better thing? First one. Error should be low, right? Cost function should be low. Okay, because cost function is the difference between the actual value. It is a function of actual value and the predicted value.
In this case, the degree 1 is a better model than degree 2.
Yes. Right?
Should we try it for degree 3, degree 4?
Absolutely. But that is where your understanding of the subject comes into picture. How much you cannot keep on trying for infinite things, right? You find a point, here itself you realize, maybe one or two you will try, then you will conclude that, degree 1 is better. Okay, let me show you the coefficients of degree 1. Okay, that will clear a lot of doubts if you have. Okay, so I might have to execute things from here. Intelligent fit. Yeah. So after this fit is done, insert below. Okay. You want to see all the, how many coefficients will be there, guys? If I do this, how many columns were there? I think 6 columns, huh? Except price, how many columns will be there? 1, 2, 3. Yeah, 6 columns. So how many coefficients will be there? Huh? 6 coefficients, because you are trying to find out, for each column, right? 1, 2, 3, 4, 5, 6. Is it clear? Similarly, in my last case, what will be the number of coefficients? 28. Got it, right? Because you have derived features also here. What is it in case? Yeah. So can you tell me how it is 28? How? From 6 column, how it became 28 columns? I didn't reshape it. Huh? No, there is no magic, right? So we had 6 columns. Yeah, of course we did transform, but with degree 2, how many columns were there? 6 columns were there. I will not write all of them, write few of them. Okay, suppose you had 6 columns, huh? Say the column names are x1, x2, x3, x4, x5. These were the 6 columns. You are telling degree 2. For these 2 columns, degree 2 polynomial will be what, a, b, a square, b square, ab. Understood? For 6 columns, how much it will be? Of course, individually it is there. Then x1, then x1, x2, then x1, x3, then x1, x4. Okay, then x square, then x1 square, then x2 square. All these things will be part of it. Got it, right? So just why, and you might think why these are column names, right? Then you are thinking in terms of it. If x is square footage and bathroom, okay, then why are you multiplying them and why is that important? Understood, right? If x1 and x2 are your X1 is your price square footage column, X2 is the number of bedroom column. Why is X1 into X2 important in defining the feature, in defining the prediction, in doing the prediction? Take this a small example of sugar, and this is how I explain to everybody. Suppose you want to predict how much sweet is your coffee. Simplest example, once I was facing difficulty. So this is sugar. This is stirrer. You know what is a stirrer? And sweetness. Right? You have to see. So you say you are adding 1 teaspoon of sugar. You are stirring it once. Not stirring. You are using stirrer. What will you say? So what is it? So you have stirrer. Stirrer is one thing, right? Okay. So if you use stirring before you add sugar, does it make your coffee sweet? Understood? So there is a derived feature that you need. Okay, there is a derived feature you need, stirrer after sugar. Understood, right? So this is derived feature. Okay, and that is why derived feature is important. So similarly, this is what we can think of. But generally, in your complex data, there are a lot of derived features that we might not be able to think of. That is where it comes into picture. Okay, go through this video like 1 to 2 times minimum. Okay, understand why straight line. Actually, watch the previous video, the Friday's video. People who have not revised it will find this class impossible to follow. Okay, go through that video. Go through this video. Write code. Take pen and paper. If you have any doubts, please let me know. Okay, because this is the foundations of it. I told you initially, right? It will spike up. This is the point. It is spiking up. Okay, go through them all, and I have to leave. Okay. So this is what is the comparison that you take at the end. Okay, we have degree 1, degree 2, and you realize degree 2 is better. Right? That is the end conclusion that you have. The first one was simple, right? Where we didn't pass any polynomial features. Okay, and this is degree 2.
Error is small.
Degree 1 error is small. 14,000. Okay, so degree 1 is better than your degree 2. Got it, right? Okay, go through it. Okay, I could have skipped a lot of details, frankly, but at least what you try to revise it and try to understand as much as possible. Okay, so if you remember last time we discussed about gradient descent, dy dx, all those things. Please revise that. Okay, try to hear this out. Okay, if you understood why did I break test and train, splitting the data into 2 parts. I discussed about overfitting. Okay, I discussed about how do you what is a vector in n-dimensional space. Okay, so whatever I discussed today and previous class, this is more of a topic of one book. If you see linear regression, you'll at least find me touching all the topics there. But again, that the thing that happens with so much of details, it might become heavy. Okay, so just go through that. Let me know if you face any problem. Okay. Okay, it is obvious to not understand a lot of things. So feel free to speak out as of when you find it is difficult to understand. Most of other people will also have the same problem.
These last 2 statements, are these more of maths concept?
Which one?
Like the train X, train Y?
No. This is not. This is hypothesis testing. Okay, you're validating the hypothesis that you made. Okay. So not. So, please don't discriminate maths here. Okay. I generally say in the beginning it is good to know, but it is definitely. If you're planning a career out of here, okay, don't expect your interview to skip you without asking maths.
Because I just wanted to have an.
No. I'm just telling in general. Okay, there are some folks in other maths, and they actually avoided the learning part. But it impacts because we are not here for fun, frankly, right? It is here for serious career. So things are not easy. Okay, but for my job is to give as much as details, try to sink in. Okay, go through them one time, another, and feel free to ask any doubts that you have.
All the videos.
All the videos. I'm putting there in this video also. Let me end it. Stop recording.